Okay, so it's our great pleasure to have Coral Jones today. So he is an assistant professor in the Department of Mathematics at North Carolina State University. He got his PhD in 2016 from Vanderbilt University under the supervision of Paul Jones. His research interests encompass compact quantum groups, so quantum symmetries, tensor categories, subfactor, planar algebra, quantum groups, and operator algebra. Correct, please.
Okay. Okay, great. Thank you so much for the invitation and for the introduction. Um, I really hope to visit BIMSA someday in person. I've heard really good things. Okay, but please feel free to interrupt me at any time if you have questions about anything I'm saying. So, is it correct that the seminar is an hour and a half long? Is that right?
Up to 1 hour for your talk, and then up to half an hour for the question.
Okay, okay, perfect. Okay,
But
that
you,
sounds good. Yeah. Okay, good. Okay, great. What I wanted to talk to you about today is this idea of categorical dualities of spin chains. So first, I wanted, before I could define, what categorical dualities are and set up the mathematics problem that's in here, I wanted to kind of give an overview of the operator algebraic approach to studying quantum spin systems and the thermodynamic limit. And the talk today is going to be focused on the case where our space is actually just Z. So often people consider spin chains on a lattice Zn or maybe on some other type of graph, but we'll just stick to one dimension. So we'll be working on Z here. And the idea is that you have a local finite dimensional Hilbert space given by C to the D. So often, you can pick D equals 2. So we just have a system of qubits floating around. And when you have this local Hilbert space, you can define the local Hilbert space associated to an interval. So if I take an interval inside Z, I can define the Hilbert space associated to that interval by just taking the tensor product of this on-site Hilbert space, and the different factors of this tensor product are labeled by the points in your interval, right? Because intervals are discrete here because I'm working with Z. And so that's your Hilbert space that you can assign to an interval. And so from that, you can also define the local operators. So these are the operators of your quantum system that are localized in that interval. And it's just all the bounded operators on this local Hilbert space, Ki. And of course, since these are finite dimensional Hilbert spaces, this algebra is actually isomorphic to the tensor product of the D by D matrices, where the different tensor factors in this tensor product are indexing the sites that the operators are localized at. So we have associated to every little interval in Z a nice finite dimensional C-star algebra. And in fact, it itself is just a matrix algebra. But they kind of get larger as the intervals get larger and larger. And in fact, we have a natural way to compare these algebras associated to different intervals. So if I take one interval I inside another one j, then I have a natural inclusion from the algebra of operators localized in I to the algebra of operators localized in j. So if I draw kind of this picture for operators localized in I like this, then this inclusion looks something like this. So I just take this operator and I fill in identity strings, around the the operator here. Okay, so here's my little subinterval I. Here's my big interval j. And so operators that are localized in I can kind of be thought of as subalgebras of operators localized in j by just putting these identities everywhere. And so you don't just have, one operator algebra for every interval, but you have this system of algebras indexed by these intervals that are all kind of included into each other in a nice way. Um, okay, and so that's kind of the basic setup. You don't just have a single operator algebra, but you have all these operator algebras indexed by intervals that are related to each other in natural ways. And so what you can do is you can define this algebra of local operators by just taking the kind of union over all the intervals of these a sub i's. And technically speaking, this should be some kind of co-limit for those of you who are categorically minded. You take the co-limit of all these inclusions, and you build this big algebra. And if you want to, you can actually complete this. There's a unique C star norm on this algebra, right? This is essentially a UHF algebra. So you can complete this in the operator norm and obtain a C star algebra called the quasi-local algebra. So this is the completion. This is called the quasi-local. Okay, and for the purposes of today's talk, you can really use either the quasi-local algebra or this is what I might call the local algebra, the uncompleted version. It doesn't actually matter for the purposes of today's talk, but in general, when you're doing spin systems, you really need the quasi-local algebra. Okay, and so this is kind of what's called the kinematics of the spin system, namely the structure of the observables, like what I can measure, where it's localized, this sort of stuff. But to really have a spin chain, you also need a Hamiltonian. Okay, and so what we're interested in are what we would call local Hamiltonians. Okay, and so what is a local Hamiltonian? So I'll write this informally first. So it's going to be an infinite sum over all intervals inside Z of these operators HI, where so first of all, this HI should be localized in I. So it's in this subalgebra of operators localized in the interval I. Okay. Two, each of these HIs should be self-adjoint, so they're equal to their own star. And three, there should exist some R such that HI equals 0 if the size of I is bigger than or equal to R. So what this means is that the terms in this sum, even though the sum is over all intervals inside Z, it's going to be 0 if the intervals are too long. So it's over. So kind of the intervals that actually give you a non-zero contribution in this sum have to be of bounded length. Okay, so that's this is crucial in making everything work, and this is what's called a local Hamiltonian. So the first thing you're going to notice, as mathematicians, is that this infinite sum doesn't converge, right? Like there's no sense that this sum is actually a well-defined operator. So what are we even talking about here? Well, the point is associated to this data. So a physicist might write this as an infinite sum, but associated to this data, you actually can get a well-defined derivation on the local algebra. So you can take this h and define delta sub h of a to be the same sum over intervals in Z. But now I take the commutator of these HIs with my operator A. And here A is some local operator. So maybe it lives in some A sub j. And the point is that actually, since I have this bound on the support of the terms in the Hamiltonian, this reduces to a finite sum for any local operator. Right? Because A, since it's localized in some interval J, will actually commute with all of the terms in the Hamiltonian except finitely many that overlap, whose supports overlap with J. So even though the operator H there's no sense in that converges. This derivation on the or this operator defined this way actually does make sense on the local algebra, and this is a derivation. It's easy to check just because it's defined with commutators on a loc. And actually, as long as the norms of the local terms are bounded, you can actually integrate this onto a time evolution on the quasi-local algebra. So you can actually define if you define sigma t of a equal to this infinite sum n equals 0 to infinity. Let's see if I can get this right. I t delta sub h to the n over n factorial of a. This actually converges and it defines a one parameter automorphism group. So this is time evolution. But now, normally in quantum mechanics, time evolution is a unitary on a Hilbert space. But in this algebraic perspective, in the thermodynamic limit, it's actually an automorphism, automorphism of the quasi-local C star algebra. Okay, so if you're used to quantum mechanics, where you have basically a Hilbert space and the Hamiltonian's an operator on the Hilbert space, and time evolution is you do e to the it u. This is kind of like there's an equivalent version of that where you use the algebra of all operators on that Hilbert space called the Heisenberg picture. And this is a generalization of the Heisenberg picture, or, kind of it's like locally we have the Heisenberg picture, but then we're taking this kind of infinite degrees of freedom, almost quantum field theory like extension in the thermodynamic limit. and you can't talk about necessarily unitaries on a fixed Hilbert space, but it's better or more universal to talk about automorphisms of the algebra. And so that's how you deal with time evolution. And so this is the basic setup, I guess, of quantum mechanics for spin systems on a lattice. So that's maybe where I want to take a pause and ask if there are any questions about the basic setup. So this is kind of the operator algebraic approach to spin systems on the lattice.
In fact, I have a question.
Yes.
So you take the set Z of integers and an interval. When you consider, for example, conformal net, usually you take an interval in the circle. So the circle is a Fourier, is a dual of Z. So is there a link with conformal net or something?
Yeah, so that's a very interesting question. So the idea is that these abstract spin chains, so we're going to get more general than what I just defined. What I just defined is almost like a free version of this. But yeah, these things are supposed to be almost discrete analogs of conformal nets. So, they lose a lot of the interesting stuff that conformal nets have, like diffeomorphism, group symmetry, and stuff. But there's a lot of structure that's similar. For example, there's a DHR category and all this kind of stuff going on. So these sort of things are indeed analogous to conformal nets, but it's an analogy, and it's not clear if there's any kind of direct connection or anything yet. Although, some people hope that by taking a spin chain and doing some kind of renormalization group flow for the spin chain at some critical state, you might get a conformal net, but no one's been able to do that outside of a couple examples. Yeah, but that's a great question. Yeah, spiritually these are very similar, and indeed, a lot of my approach to what I'm going to tell you about today is taking lessons from the mathematical theory of conformal nets and trying to apply them in this kind of context. Okay, good. So that's the basic setup. And so let me give you an example, which will be the most important example of this sort of thing. And so this is a version of the Ising model. Okay, it's actually technically the Ising model, the quantum Ising model with what we say is in transverse magnetic field. So I'm going to define a Hamiltonian. So here my local Hilbert space is C2. So I have a bunch of qubits everywhere. Okay, and so my local operators that are acting on a single sites are 2 by 2 matrices. And then if I act on an interval, it's I have tensor product of 2 by 2 matrices. And so just to remind you, there's a nice 2 by 2 matrix. The poly X matrix, is basically implementing bit flip, right? And then we have the poly Z matrix, which acts diagonally on the standard basis of C2 with 1 and -1. And then you can define the Ising model. It has actually two parameters associated to it. One of them is called J and one is called H, and they're just real parameters here. But we take the J times, or maybe I'll say it this way, the sum over I in Z of J times sigma I Z. So let me tell you what this means here in a second. Sigma plus Z plus the sum over H, again, I in Z of sigma I X. What I mean by sigma I X, or sigma I Z, sigma I plus 1Z, is I mean the copy of sigma Z acting on the ith site. So if you were drawing little tensor network pictures, I would put like a sigma Z here, and this would indicate the ith site. That's what I mean by sigma I Z. Like this notation means I'm actually talking about that thing. Okay, and similarly for sigma X and sigma I plus 1. Okay, so that's this notation. And so these are kind of my local Hamiltonian terms, like my HIs. There's terms for intervals for intervals of length 2, right, nearest neighbor intervals, and that's this term here. And then there's terms for intervals of length 1, single points, and then there's no other kind of term. So there's kind of a bounded diameter on the support of the terms in my Hamiltonian. Okay. And so this is a canonical example, and this is actually a quantum Hamiltonian. So the classical Ising model is basically the same thing, but I make this also sigma Ix, I make it sigma Z. And then everything commutes, and so it's essentially a classical Hamiltonian. But because I put a sigma X here, it doesn't commute with the sigma Z's. This is a quantum thing. Okay. And so that's what's going on. Okay, so this is a canonical example. So what we're interested in is studying various equivalences of Hamiltonians. Okay, and there's many different things you could mean here. And in the condensed matter literature, it depends on the kind of thing that you're talking about. So one of the things that's very common to do is to consider gapped Hamiltonians. And so these would be Hamiltonians such that when you look at a ground state representation and you think of your Hamiltonian as an operator, there's a gap in the spectrum below the lowest, energy eigenstate, and then the rest of the spectrum. And then a natural equivalence relation to consider there is you kind of deform your Hamiltonian through the space of all possibilities, and you keep the gap open, and you get an equivalence relation there. And that's useful for studying gapped phases of matter, but it's not very useful for considering just generic local, equivalences between local Hamiltonians. And so there's another natural notion that it's not actually clear how it's related to that gapped Hamiltonian, but it actually makes sense much more generally. So if I have two Hamiltonians on my same, I'll assume for now that they're on the same local algebra. So I'll say H and H prime are Hamiltonians on I'll say on A. So A is one of these kind of UHF tensor product algebras that we described before by taking the tensor product of these sites. An equivalence between them, what is it going to be? Is an isomorphism, or I guess an automorphism because they're the same algebra. So it's an automorphism of the big algebra, alpha from A to A, okay, such that it better intertwine the two Hamiltonians. And to intertwine the two Hamiltonians, the Hamiltonian is really reflected by the derivation that you get from it. So I'll say something like this. If I do alpha and then I do delta H, which is, remember, the kind of the derivation associated to taking the commutator with the Hamiltonian, this should equal to alpha composed with delta H prime. So it intertwines the two things, but that's not quite enough because we want this alpha, which I'm thinking of as a manifestation of a unitary, but just in the thermodynamic limit. So it's an automorphism of the quasi-local algebra. I want this to preserve locality in a certain sense. So let me write down what that means. There should be some R bigger than 0 such that if I apply alpha to operators localized in some interval I, this should land in the algebra of operators localized in the interval I plus R, where here I plus R means the following. If I is an interval, then I plus R is just this bigger interval where you add R to both sides. So it's basically like the R ball of I, right? So you kind of take I and you make it R bigger in both directions, and that's I plus R. So it's not really shifting by I. It's kind of bad notation. Apologies. But yeah, you just kind of take the R ball of I. And the point is that this R should be independent of I. So even for really large intervals, if I take an operator localized in that large interval and I apply alpha to it, it should be localized in I plus R, but as I gets large, kind of the ratio of R to I is small. So it kind of, in the limit as things get big, you're thinking of this R as being kind of like a small error or something. Okay? And so what you should think of this alpha as, it's an automorphism, but we don't really think of it as a dynamics on the system. It's not like a time evolution or something. It's more like a change of variables. Okay, I'm thinking of this alpha, this automorphism, as taking an operator, which is one of the variables of my theory. It's an observable, and I'm applying alpha to it, and I'm getting a new observable. And I'm making this identification between observables that will intertwine the physics as described by the Hamiltonian, and will particularly intertwine the time evolutions and these sort of things. But it's doing it in a locality-preserving way. So it's saying that I'm doing a change of variables, but if I'm looking at an observable that's localized in some region, the change of variables observable will be localized in a region not too far away, in a uniform sense. Like this R is the same R everywhere. So that's kind of what you're thinking of when you're thinking of how you should think about this equivalence relation. Okay. And so this leads to the following definition. An automorphism, alpha from A to A, that satisfies 2. So here we're just kind of forgetting about the fact that it was supposed to intertwine two Hamiltonians, and we're just looking at the automorphism from A to A that has this property down here. Is called a quantum cellular automata. Quantum cellular automata. Okay. And then that's just a definition. It's kind of like if you took a classical cellular automata and you applied the Gelfand dual like Gelfand duality to get a definition for, a quantum cellular automata or like a non-commutative cellular automata, you would end up with something like this. But then in quantum mechanics, all of our, time evolutions and stuff are supposed to be unitary, so they make it an automorphism instead of just like an endomorphism. And so that's how you get the definition of quantum cellular automata. It's really just applying the Gelfand duality philosophy to get kind of an obvious notion of a non-commutative version of a classical cellular automata.
Yes, you have a nice question.
Yes.
Can you make a quantum, what's the name? Uh, Game of life. You know the game of
Uh,
life.
yeah, good
Quantum.
question. So you can't do a direct quantum game of life, but you can write down quantum cellular automata that have interesting behavior like the game of life. But you can't directly do the game of life because that's not unitary. So most classical cellular automata are not invertible. So they're kind of different. They have a different field in quantum cellular automata because you can't reverse them. But nevertheless, there are still some interesting quantum cellular automata. But I don't think probably if you Google it, someone has written down some quantum cellular automata that they call the quantum game of life. Wouldn't be surprised. Okay. But somehow there's not a direct obvious analogy because of this invertibility condition. So the local rules, it's pretty hard for those. If you just write stuff down with local rules, the dynamics you get, it's pretty hard for it to be an automorphism of the algebra. Usually you just get an endomorphism of the algebra. And so it's pretty hard to make it. Okay. Yeah, good. Okay, so that's what a quantum cellular automata is, and it's a natural object because it gives you a natural equivalence relation between two local Hamiltonians. So in other words, you can think about this group. It turns out this is a group just under composition of automorphisms. This is a group of quantum cellular automata, and it acts on local Hamiltonians. And when you're studying these local Hamiltonians up to equivalence, you're really trying to understand the orbits of the space of local Hamiltonians under this action by quantum cellular automata. Okay. But there's kind of like a little sub thing. There are these things called the trivial quantum cellular automata. I'll put this in quotation marks. These are highly non-trivial, and QCA means quantum cellular automata. But they're kind of trivial in a sense of phases, because if you're related by this kind of quantum cellular automata, there's kind of a nice continuous deformation you could do to get from one Hamiltonian to another if you're related by these trivial QCA. So these are kind of like the topologically trivial QCA. And how do we describe them? They're what are called finite depth quantum circuits. So first, let me define a depth one circuit. Okay, and the idea here is you partition Z into intervals, into disjoint intervals. So for example, the standard example is I'll take Z and I'll do like some nearest neighbor partition. So I'll put these together, put these together, put these together, put these together. And this should be, the length of the intervals in the partition should be uniformly bounded. So I'll say a bounded partition. But what I mean by that is the lengths of the intervals, the sup over the whole partition is finite. Okay. And so here, this is good. This is a partition into nearest neighbor, so all the intervals have length too. And I'll call this partition, I'll call it like I sub I or something. And then you pick a unitary U sub I that lives in the algebra of observables localized in the interval I sub I. So basically, for each of these nearest neighbor things, I pick some unitary sitting here. So if this is like I sub 1, I pick some U sub 1. I pick some unitary U sub 2 sitting here. And so I pick some unitary localized at each of the intervals. And then I define an automorphism of my algebra by just conjugating by the big infinite product of these U sub i's. Okay, and so first of all, this doesn't make sense. So I have to explain what this means, but I take the product of the U sub i's and I conjugate by it. And again, so this is kind of in quotation marks, because this infinite product of unitaries, this is infinite because this partition of Z is infinite. So yeah, I should say partition Z, partitioning the whole of Z into these disjoint intervals. And so this is an infinite product, and as we know, an infinite product of unitaries generically doesn't converge. But the point is that A will commute with all but finitely many of these UI terms, right? Again, we're in this situation. So here's a picture. I have like my A here. It's localized somewhere. And then I have this nearest neighbor's unitary, for example, like sitting over here, right? And I'm applying this infinite product of U, sitting. Okay, but I'm conjugating by these. So I have U stars sitting. Oh, I didn't say I should put stars there. So I have my U stars, and here I'm just kind of assuming all the unitaries are the same for convenience. But you can see that, except for finitely many that kind of interfere with the A here. So here are my finitely many that interfere with the A sitting around here. These all cancel out, right? These cancel and they'll cancel. So even though it looks like there's some problem because I can't define infinite product of unitaries, I just all but finitely many will cancel each other out. And so this actually does give you something that's well defined. Okay. And this thing has bounded spread, or it satisfies this kind of QCA condition, because if I take this operator and I conjugate by it, it's localized in this little region, but that region is not bigger than the diameter of the largest interval that I picked. So because I made the partition uniformly bounded, when I conjugate by these unitaries, there's kind of like a little light cone associated to my operator, how far away the new operator can be, how much bigger the support of the new operator can be compared to the old operator. And it's basically determined by the diameter of these intervals. Okay, and so this is what's called a depth one circuit. These are kind of boring because I'm just running a bunch of quantum gates in parallel with each other, morally speaking, in the thermodynamic limit. Where this gets interesting is when I compose these with each other. So instead of just taking one layer of a circuit, I then take another layer of circuit, and the partitions don't have to match with the old partition. And that's where interesting stuff can happen. So let me let me actually copy this picture and move it to the next page so I don't have to draw it all over again. Let's see. Let's see. B. New page. Okay. Paste. Good. Okay. Good, good. And so the idea here is now I can take another depth one circuit, but maybe associated to a different interval. So now I have another layer of unitary gates sitting over top, right? And a similar layer on the bottom. And now something more interesting is happening because I'm not just running a bunch of gates in parallel, and my light cone kind of expands a little bit, but there's still a light cone. So this would be like a depth two circuit because it's a composition of two depth one circuits. And so you can define a finite depth circuit in this thermodynamic limit language is a finite composition. So it's a composition of depth one circuits. So here you go. That's an example. And then you can keep going. And there's not you don't have to use nearest neighbor intervals. That's just a convenient picture to draw. You can use arbitrary kind of partitions as long as the size of the intervals stays uniformly bounded. Okay, and these are kind of trivial because it turns out that in the space of QCA, if you think about this with various topologies, if you look at the kind of component that's path connected, the path connected component of the identity in the space of QCA with appropriate topology, it ends up being the finite depth circuits. So these are the ones that are kind of deformable to the identity automorphism kind of within the space of all QCA. And so in some sense, these are trivial. And so a natural question that arises when you're studying these things is what is this group of QCA? Of course, and this depends on your quasi-local algebra, which in this setup that we give depends on D, right? So depends on the dimension of the local Hilbert space here. But you take this QCA and you modulo finite depth quantum circuits because it turns out it's not completely obvious, but finite depth quantum circuits is a normal subgroup of QCA. And so you can take the quotient. And you can ask, what is that? Like how far away are these circuits, which are kind of trivially or deformable to the identity automorphism? How far away is that from being everything? You could imagine actually that this was everything. And I think actually this was a surprise, the fact that this wasn't everything when this originally the fact that this group is non-true. And so I'll tell you the answer. So this is a theorem due to Gross, Nesmith, Vaught, and Werner, commonly called GMVW. And it's the following. They don't say it this way, but this is my kind of mathematician's rendering of what they actually said. So if this, of course, depends on D, this actually is the group of, so let me explain what this is. So you take the ring, so take Z as a ring and adjoin 1 over D, and then take the ring generated kind of by 1 over D inside, inside the rationals. So it's a subring of the rationals that has Z and it has 1 over D, and you take the ring generated by that, and then take the group of units in that ring. So you take the multiplicative invertible elements in that ring that I just described to you, and it turns out that's actually isomorphic to this group of finite depth circuits. Okay, and so that's that you can kind of classify QCA up to finite depth circuits, which means up to kind of topological equivalence, because the finite depth circuits are exactly the topologically trivial ones, the ones that can be deformed to the identity. So kind of the path components of the group of QCA is isomorphic to that. Where remember, D here is the dimension of the local Hilbert space. Okay, so that's kind of old stuff. And then so this is all just basically spin systems, equivalence, blah blah blah. And now what I want to do, if all of this makes sense, is to talk about dualities. But first, do we have any questions about what I've said so far?
This quotient isn't that translations?
Yeah, right. So this quotient contains translations. And here's a great example of a QCA. Shift everything to the left. Okay, and that generates a subgroup of this group here, which is multiplied by D, which is invertible in this ring of 1 over D. But then there are all these generalized translations. So if you take D and and it factorizes into a product of P and Q, say, then the matrix algebra, D by D matrices, factors into a tensor product of the P by P and Q by Q matrices, and you can like shift the P's to the left and the Q's to the right. And that actually gives you what's called a generalized translation. So you do some factorization of the local algebras and then translate possibly in different ways, and that saturates this index. So everything is a generalized translation. Often people also consider this up to stabilization, where you add ancilla locally at every site, and then this whole thing collapses down to being just like Q or something because you're throwing it all together. But that's not the equivalence relation we're considering. Okay. Good. Yeah. So that's a really good point. Basically, in 1D spin chains, everything is what's called a generalized translation, which means up to some factorization, it's kind of like you're factorizing and translating some of the components into factors, and that's what this is. Okay. But a duality. So what is a duality? And so when I say duality, the thing I have in mind are dualities of Kramers-Wannier type. So duality means so many things, especially in physics, but also in math, right? But there's a special kind of duality that's the model for the kind of duality I'm talking about, and it's called Kramers-Wannier duality. So Kramers-Wannier type duality. And so here's the idea. So instead of just taking my quasi-local algebra, I'm going to say there's some subalgebra of the quasi-local algebra, and it's going to be nice in the sense that it's going to have like local pieces that live inside the local pieces of. Oh, it seems that my pencil stopped working. Just give that a quick grind. Yeah, so we're going to be looking at these subalgebras. And the idea is, while my pencil is taking a quick extra charge, I thought I had charged that. So hopefully it's just the charge, maybe it's the. But the idea is that often this subalgebra will arise from some symmetry. So maybe I have a group acting on my big. Imagine like I'm doing spin flip and I have it acting on all the sites. Or maybe I have something more interesting like a Hopf algebra or weak Hopf algebra or matrix product operator algebras or something acting on my whole spin system. Or maybe some algebra closely related to that spin system in the case of matrix product operator algebras. And you look at the invariant operators sitting underneath. So that's the kind of subalgebra that I'm imagining, is that I'm having some symmetry and I'm looking at the operators, the local operators that are invariant under that symmetry. So let's see. So I have this sort of thing. And the idea is that I can say that a Hamiltonian is affiliated with B if each of the local terms lives in the BI subalgebra. So not only do the local terms in the Hamiltonian kind of are they local, but they live inside this special subalgebra. Okay. So a duality, if I have two Hamiltonians, one of them affiliated to B, which is sitting inside my quasi-local algebra, and one of them affiliated to some subalgebra, other subalgebra B prime, sitting inside the same A, a duality is going to be a bounded spread isomorphism. So something like a QCA, but instead of going from A to A, it's going to go from B to B prime, and it's going to intertwine the Hamiltonians as derivations from B to B prime. So a duality is an isomorphism alpha from B to B prime such that if I do alpha and then I do the derivation associated to H prime, that should be equal to delta sub H composed with alpha. And this is on B slash B prime, or I guess this is technically this would be on, oh yeah, I put that in the wrong spot, sorry. This should be here. And so this is on B. These are both maps from B to B prime, technically speaking. So that's what. Okay, and so the idea here, so it should do that, and it should be bounded spread. So there exists an R bigger than 0, bigger than or equal to 0, such that alpha of B sub I is contained in B prime sub I plus R. So it's that same notion that we had before. So it's like a quantum cellular automata, except that when people say quantum cellular automata, they usually mean I'm mapping between from the same algebra to itself. And so it's just a slightly different. They don't have to. The two algebras don't have to be identified previously. B and B prime can be different. Okay. And so the idea here, what's conceptually going on, is that this is an equivalence between pieces of the theory that may not extend to the whole set of quasi-local operators, right? It may only be defined in a nice invertible way, at least, on this subalgebra. But generically, in the situations you care about, this subalgebra is enough to see the low energy part of the spectrum of the theory. So this gives me an equivalence between the phases associated to these Hamiltonians, even though it's not giving me a full equivalence between the spectrum of the Hamiltonians. Okay, so it's enough to be like a symmetry of a phase diagram, like it maps this phase diagram to that phase diagram or whatever, this component to that component, without actually giving me a full equivalence. So, I kind of think of it as like a hidden equivalence. It's an equivalence that you can only see when you pass to the special subalgebra. Okay, and it's not clear if you just give me a Hamiltonian, there's not like a unique subalgebra B to pick that contains all the terms. Sometimes there's some obvious choices, as we'll see for the Ising case. That's going to be our main example. But it's more of an art than a science picking the appropriate B. So you could have different dualities involving the same Hamiltonian, by picking different subalgebras B that are affiliated with your Hamiltonian. Okay, so to get a sense of what's going on here, let's revisit the Ising case. So remember, I had this Hamiltonian H sub j comma H, which was the sum J sigma I Z sigma I plus 1 Z plus the sum H of sigma I X. Good. Okay. So the idea here is that the subalgebra, so there's a Z2 action on my algebra A, so this is the big quasi-local algebra, that basically conjugates by spin flip, right? So on each site, I have qubits, and I can swap, 0 and 1, and that gives me a unitary on each site, and so I can basically take the tensor product unitary and conjugate by it. So I'm just conjugating by spin flip on every site, and that gives me a nice Z2 action on A. And then I can define the local algebra B sub I to just be the local operators from A that are fixed under this Z2 spin flip action. So it's the fixed points. Z2 fixed points. So Z2 operators. Okay, and if you actually, so I'm basically applying a sigma x, a product of sigma x's everywhere, and I'm conjugating by it. It's a depth 1 circuit, right? Like where my partition is just into single points, and I'm putting the sigma x at every site. That's a unitary, the spin flip unitary, and I'm using that depth 1 circuit. That's my symmetry. Okay, and the point is that actually each of these terms is symmetric. Okay, obviously this one's symmetric because I'm applying sigma x's everywhere. I'm doing spin flip, so spin flip commutes with spin flip. This one's symmetric because even though each sigma x anti-commutes with the sigma z on the same site, I have two sigma z's next to each other. So the signs will cancel out. And so actually both of these terms are symmetric. And so this Ising Hamiltonian, or Ising, I never know which one to say. I think people say both, depending on if they're German or not. but this Hamiltonian, in the sense we were just talking about, is affiliated with the subalgebra B, which is the fixed points under I. Okay. So here's Kramers-Wannier duality. So this is the famous KW duality. So the idea is that actually this B, you can think of it as being generated by the terms of the transverse field Ising model. So it's actually generated by operators that look like this and by operators that look like that. And so you can define an isomorphism alpha that does the following. It sends these terms to this sigma ix, and it sends sigma ix to sigma I minus 1z, sigma I z. Okay? So you can check, it's not obvious, but you can check this actually defines a bounded spread isomorphism of B. Okay? That kind of, it's like a half shift because the sigma z terms are kind of mapping to sigma x's with the I, but the sigma I x's are mapping to the double sigma z terms, but shifted down by one index. Okay, so this is kind of it has some spread. There's a little bit of a shift going on, and indeed, if you do this twice, you literally just get the shift down by one. Okay, so this is kind of like a factorization of a translation operator. And the point is that if you take alpha of delta sub h with the two parameters, it intertwines the Hamiltonian where the parameters are switched, right? That's the basic idea. Because if you look at the Hamiltonian here, this Ising Hamiltonian, well, I'm replacing this with the sigma x, right? And I'm replacing this with the sigma zz's, right? That's what my automorphism does. It basically swaps these two terms here at the cost of a shift, but I'm summing over everything in my commutator, so it does the same thing. And so it has the effect of interchanging J and H. Okay? So it's kind of giving you a symmetry of the Ising Hamiltonian with different parameters, and it becomes a genuine symmetry at the fixed point, or at the point when J equals H. Then it becomes a genuine symmetry of the symmetric Hamiltonian. But the key point is that alpha does not extend to the whole A. So that's what makes this kind of a non-trivial duality to A, at least as a bounded spread isomorphism. It does not extend in the way that into an equivalence. So it does not extend to A as an equivalence, as we previously defined. So you can only see this kind of equivalence on this symmetric subalgebra under the Z2 symmetric subalgebra. And so that's the essence of a duality, is I have some kind of equivalence that's a bounded spread isomorphism on a subalgebra containing the terms of the Hamiltonian that intertwines the Hamiltonian that does not extend to an equivalence in the sense as we've defined on the whole algebra. So that's basically what we mean by duality. Okay. So that's the setup. And so now we can go abstract. Yeah, go ahead.
Yeah, so in the previous slide, the KW duality has a non-invertible. It's non-invertible, right? So you square it and then it's...
Yeah. So it's non-invertible on the big algebra, but it's an isomorphism. It is definitely invertible on the symmetric subalgebra. So when I say squared is translation, I mean on the symmetric subalgebra. Yeah. So alpha is only defined on these operators. It's not defined, like it doesn't send anything, doesn't send sigma iz to anything, because that's not an element in the symmetric subalgebra, right? Okay. It only is defined on the symmetric piece. And so in this version of duality, so a lot of people, so I should mention this, who study dualities, think about the key point that they're focusing on is that this is not invertible. But the key point that I'm focusing on is that it is invertible on the symmetric subalgebra, and that's what actually makes it a duality. And it's not invertible on the whole thing, that's true, but it wouldn't be a duality if it wasn't invertible on some symmetric subalgebra containing the Hamiltonian terms. Like, that's the point that makes it actually be an equivalence in any sense at all. But yes, indeed, it is an example of a non-invertible symmetry, because you always can extend these two quantum channels on the big algebra. that restrict on the subalgebra to be this bounded spread isomorphism. And those quantum channels are not invertible, indeed, and they can't be invertible. And indeed, part of the theorem that in the paper that I don't think I'm actually going to state this theorem in this talk is a criteria for when these things actually extend to invertible symmetries on the whole algebra. Like you can get a nice categorical criteria, and this definitely fails that criteria. This can't extend to an.
So using, like, just to summarize, using quantum checks, like this more generalized notion of like not just homomorphisms, but this bigger thing, you're able to compute, let's say, in some example, what spoils the invertibility when you try to.
Yes, exactly. There's a crisp categorical obstruction to exactly doing it, and that's kind of the point of the paper is if you have the bounded spread isomorphism on the subalgebra, you can compute. There's a homomorphism to some group, and if the image of that homomorphism satisfies some property, then you can extend it, and if not, then you can't. And this group is like some nice finite group that you can, like it's a group of braided autoequivalences of a category.
Of fusion, right?
Of a fusion category, yeah, exactly.
I see. Okay. So that makes, like, you have to consider gap systems in that case.
Well, no gap systems here, because the point is I'm just in a 1D spin chain, and so I'm going to extract a so I take this symmetric subalgebra. Okay, this symmetric subalgebra has a braided tensor category of DHR bimodules associated to it. Okay, but there's no states. I don't care about actually Hamiltonians. I've actually forgotten about the Hamiltonians. So there's no gap to anything. I'm not talking about 2 plus 1D topological order or something like that. If anything, this is kind of like stuff happening on the boundary of a 2 plus 1D topological order.
Exactly.
But it's a 1D thing, and there's no gap per se because I can have gapless boundaries on 2 plus 1D topology.
But you need the alpha to intertwine between the.
Yeah, you do, but they of course don't have to be gapped. Like easing with transverse field is not gapped. But there's still a fusion categorical thing going on here because this symmetric subalgebra actually remembers the Drinfeld center of XZ2. That's part of the thing I'm going to tell you about. So from this symmetric subalgebra, you can recover the category Drinfeld center of XZ2, and this Kramers-Wannier will implement EM swap on that thing. And that fails the obstruction of preserving algebra. So there's a whole story here, but you don't actually need gapped Hamiltonians. Like this easing with transverse field is the example. Like it's a symmetry even at the critical point there. But the fusion categories come from the algebra of observables, not from the Hamiltonian. That makes sense.
Okay.
The symmetric algebra of observables.
Yeah.
So maybe it will make more sense in a second. So maybe it'll make more sense. Yeah. Okay. So let me yeah. So let me say, so the idea here is we want to abstract this situation, like what kind of thing is this algebra B that played the role in this case, like it was the symmetric operators. What kind of thing is this? And it should be an abstract spin chain. So let me tell you what that means. This is a new definition. So one, I need to assign for every interval inside Z, I have some finite dimensional C star algebra. B sub I, this is a finite dimensional C star algebra. Okay. Two, if I is inside J, I want to have an inclusion of my BI sitting inside my BJ, just like in the regular spin chain case. If I and J are disjoint, I should have that these two algebras of operators commute with each other inside the bigger, algebra BI union J. And this is an important one. If I define B to be the quasi-local algebra, so it's like the algebra I get from doing this, and I complete this, then when I take the relative commutant inside this algebra, BI complement prime intersect B, so this is all the quasi-local operators that commute with all the operators localized in the complement, this should just be BI. And so this is a version of what's called in AQFT world Hog duality. So this is what I like to call algebraic Hog duality. I'm not taking a commutant of all operators on a Hilbert space like you do in AQFT, but it's just relative to this quasi-local algebra that you need this. And you only need it for finite intervals here. And this is the complement thing. So it doesn't work if you replace intervals with their complements. You need the finite intervals living on the right side and the kind of complements. So this is an abstract spin chain. And this is the definition of one of these things. And so, you can ask the following question, given abstract spin chains, B and B prime, you can talk about what are bounded spread isomorphisms, bounded spread isos. And then you can ask about this up to, and you can also ask it up to finite depth circuits, because you can make sense of finite depth quantum circuits in this setting, just like you can make sense of them in the other setting, right? You pick a unitary, but now the unitary should live in this subalgebra or in this app. So now I'm not thinking of these algebras as necessarily being embedded inside some big spin chain thing, although that's where the applications come in, right? You actually want to consider when these algebras are inside there. But you can ask this question about bounded spread isomorphisms between abstract spin chains as abstract objects. So what are the canonical examples of these abstract spin chains that we want to know about? And there are the main example are what are called fusion spin chains. Okay, and these are basically examples that come from subfactor theory. And they're just from subfactor theory. So you let C, and so this is partly where the fusion categories come in. So let C be a fusion cat, unitary fusion cat, and you pick an object in C, and now you define the abstract spin chain. I'll write it this way, where the local algebras associated to an interval are just defined to be endomorphisms in my fusion category of the object x to the tensor I. So this really helps to just draw the same picture we were drawing before, right? So here's my interval I. And so I just take endomorphisms here. And when I want to include them up into each other, I just take the lines to make them bigger, right? This is like my bigger interval J. And this will satisfy all the axioms as long as x should be a special kind of tensor generator called a strong tensor generator. Otherwise, it might fail hog duality in a dumb way. So X should kind of tensor generate the whole fusion category in a nice way. I won't go into it. But this is an example of a fusion spin chain. And actually, in the Kramers-Wannier case, we had a fusion spin chain. So in the Ising slash Kramers-Wannier case, that symmetric algebra B was actually the spin chain associated to the fusion category rep Z2, and the object is the regular object, the regular representation. So actually, in the previous example, we were already working with fusion spin chains. And in fact, anytime you use a group onsite symmetry, the symmetric operators are going to be a fusion spin chain in rep G. Okay. And more generally, if you use a Hopf algebra acting, then the fusion spin chain, then the symmetric operators are going to be fusion spin chain in rep of the Hopf algebra. And then if you do MPO symmetries more generally, then you can have more general fusion category symmetries appearing as your symmetries. So more general fusion spin chains. Okay. So let me tell you the short answer. So we want to classify for an abstract fusion spin chain B, we want to figure out what is I'll write it this way, but the group of QCA on this fusion spin chain, so bounded spread automorphisms, modulo finite depth quantum circuits on B. Okay, so this is kind of the same question that we asked for quantum cellular for ordinary equivalences, but now we're asking it for these dualities, for these things that live on the subalgebra. And notice I've kind of forgotten about the Hamiltonian, in the same reason that when I was classifying finite depth quantum circuits or QCA up to finite depth quantum circuits, I also forgot about the Hamiltonian there, because it's like, okay, any time I have one of these QCAs, I plug in a Hamiltonian and I get something that's kind of dual to it. So I'm not focusing on the actual symmetries of the Hamiltonians here. I'm more thinking about, okay, let's just look at the bounded spread isomorphisms up to finite depth quantum circuits. Can we classify these in a similar way to GNVW for abstract spin chains? So for example, in that rep Z2 with the C2 case where we had Kramers-Wannier, can we classify those? Or maybe more generally, if I have an on-site group symmetry, can I classify all these dualities up to symmetric finite depth circuits? And so I'm running out of time. So let me tell you the two kind of things that go into it. So first thing is with Junhui Lim, who is a PhD student at Vanderbilt. We introduced a numerical index for QCA. So it's a generalization of the GMVW index. So it's IND, and it goes from QCA of B to the multiplicative real numbers with finite depth quantum circuits in the kernel. contained in kernel. Okay. And it's based on the Jones index for subfactors, on Jones index. And it actually generalizes G and VW, which is that result I mentioned earlier, how you prove that. Generalizes G. So that's one piece of the story. So we get this numerical index that kind of, it doesn't completely classify these dualities, these QCAs on the abstract subalgebra. It does in some cases. So for example, if you take a fib fusion spin chain, then actually the index classifies everything. But you need something more in general. So this is in a paper of mine from earlier, a couple years ago. So this is a theorem, and it's the following. So one, associated to an abstract spin chain, is a braided C-star tensor category of bimodules. C-star tensor cat. Bimodules, they're called the DHR bimodules. Okay, and it's a direct generalization. So Sebastian was talking about, these look like conformal nets. Conformal nets have this, you could define it in terms of super selection sectors with representations in the ground state, but you also have this localized transportable endomorphism picture. And if you take that and think about bimodules as generalizing endomorphisms, you can write down a definition for localized transportable bimodules on an abstract fusion spin chain. And if it satisfies this algebraic Hopf duality, you prove that this is a braided C-star tensor category. And it's a full braided tensor C-star subcategory of bimodules of this C-star algebra B. Okay. Two, if I take the DHR bimodule category associated to this abstract fusion spin chain that I built from a fusion category and a generating object, this is actually the Drinfeld center of the fusion category. Okay, so that's not so unexpected. But so in other words, this abstract spin chain has a braided category associated to it. If you build your abstract spin chain from a fusion category, it's the Drinfeld center. So in particular, in that Kramers-Wannier case, there's a special braided tensor category floating around, namely the Drinfeld center of rep Z2, even though there's no like gapped Hamiltonian and topological order floating around. It's appearing from symmetry in a different way. Okay. And then three, and so here's the most important bit, is that there's a homomorphism from the QCA of B to the braided autoequivalences of this DHR bimodule category. That I'll just call it DHR, the DHR homomorphism, such that the finite depth quantum circuits are contained in the kernel. Finite depth quantum circuits contained in the kernel of DHR. Okay. And so in other words, every QCA gives you an action on this Drinfeld center in a natural way by just kind of conjugating the bimodule, twisting the bimodule by the left and right actions by your QCA. Okay. And so the upshot is that I always have this homomorphism from so I take kind of the numerical index and I take the DHR index together, and I think of this as giving me a homomorphism from QCA to the multiplicative real numbers cross the braided automorphism group, or the group of braided automorphisms of DHR. Okay, hopefully that makes sense. So you always get this, and here's the conjecture. The kernel of this is always exactly the finite depth circuits. So it always contains the finite depth circuits, but the conjecture is that this equals to finite depth circuits of B. And the theorem, which is in a recent paper with my student Kylan Schatz and Dominic Williamson, is the following. For an onsite group symmetry, where the representation is the regular representation, so if G is acting on this is generalized to Kramers-Wannier case, right? G is acting on the site, but the Hilbert space is just the regular representation of G. So this is what I would say is A of rep G. It's a fusion spin chain, A rep G, a regular rep. The object X equals a regular rep. This is true. Conjecture is true. So in other words, if you want to completely classify these bounded spread isomorphisms on the symmetric subalgebras, so these kind of dualities without the Hamiltonian, just kind of the bounded spread unitaries between the symmetric subalgebras up to symmetric finite depth circuits, you just have to compute the numerical index and the action on the braided autoequivalences. And that gives you the thing. And I mentioned before that there was a crisp categorical criteria for extending the QCA. And I didn't mention that because I'm out of time, but that's actually how we prove this theorem, is we use that criteria that I mentioned about extending the QCA or extending a duality to actually be a QCA on the big algebra. And we apply that in the group setting, and we use some stuff that people have proved about symmetric QCA to get this result. So anyway, so I'll stop there. I think that's an hour, and I will stop and we can do some questions. Thank you.
Thank you. Question?
Yeah, I have a question. Thanks for the very nice talk, Corey. So
thank you.
I wanted to.
Yeah. So who am I talking to? By the way, these are great questions.
It's Hank. It's Hank.
Okay.
Yeah. So I've like let's say I have like two questions that I can combine to one. So
okay.
I want to ask a quantum integrable spin chain, like XXZ family. Is it a fusion spin chain?
Which one? Say that again.
XXZ family, let's say.
Yeah.
Symmetry. Those sorts of quantum group symmetries. Does it fit into this set?
When you have like quantum group symmetry floating around?
That's right. Yes.
So those are almost fusion spin chains. So you can generalize the definition of a fusion spin chain to, instead of letting C be a fusion category, just let it be a unitary tensor category. So I don't require finitely many simple objects.
Right.
And then you just pick an object, which is a representation of your quantum group, and you can still build an abstract spin chain. So it is an abstract spin chain. The problem is that the DHR bimodule category is generically trivial in that case. And what's going wrong is that you're not getting to, because the fusion the object doesn't kind of contain all the objects in the fusion category at one time. You don't actually see the whole category C in a local piece. And the way that I define the DHR bimodules is all about like seeing stuff locally. So what you actually have to do, you can make that work, but you have to change the local degrees of freedom to be infinite dimensional. So if you actually require the local degrees of freedom to be finite dimensional, as you usually do, that is an abstract spin chain, but the DHR category isn't the thing you want. However, if you add ancilla at every site and you add an infinite dimensional space of ancilla at every site at the same time, that thing does have the right DHR category, and it's the Drinfeld center of all unitary representations of the quantum group, not just the finite dimensional ones. And so it's one of these big centers, like representations of the whole tube algebra of the representation category of the quantum group. But that's the thing that's supposed to be playing the role of the DHR category. So I suspect you can do a version of this story in that setting using the big version of the DHR category, but you have to add in ancilla at every site, infinitely many ancilla at every site. I don't know how violent that is for you or not, but yeah.
I see. Okay, that's very interesting. That's very good, because the result that you have, in which you just recover the Drinfeld center, it kind of tells me that you can't get like a normal spin chain, for instance, where you have a non-zero central charge. But then
So actually, good. That's good.
Yeah, if you add the ancilla, of course you can put that in.
That's exactly right. Actually, we recently had a paper just like 2 days ago on the archive with Makoto Yamashita, David Jacklowitz, and Lucas Hitachi, where we proved that an abstract spin chain, so you assume that it comes from a fusion category, it's just something satisfying these axioms. If it satisfies a couple more axioms, it's automatically a Drinfeld center. And so basically, exactly what you're saying. If you have local finite dimensionality, it satisfies this and a couple more, because the examples you pointed out will satisfy what I wrote down here. They don't satisfy the couple more technical axioms. Namely, there's these things called charge transporters, and you want which are basically patch operators in the Xiaogan-Wen language, if you're familiar with that. You want them to kind of generate the right local algebras or something like that, some technical condition. But under those hypotheses, then it's always a Drinfeld center. And so if you're trying to get something that's not a Drinfeld center, you're definitely going to need not finite dimensional local degrees of freedom, or something more violent and weird has to happen. Like there's kind of a dichotomy of those situations.
Okay, that's very nice. That's very good. I'll probably check out that paper.
Okay.
One last thing. Have you looked at the quantum Hall states?
No, I haven't. Yeah, so I haven't looked at. I have not. I have not. No, I haven't done anything. Yeah, because you're right that there's secretly a topological order. Like all of this, you can think of it as like happening on the boundary of like 11-1 model. And so everything's nice and algebraic, and the analysis is simple. But for quantum Hall states, the analysis gets scary for me, so I kind of drop out. No, I haven't.
I think there's a nice way to make quantum Hall fit into this framework, especially the
Okay.
framework. Yeah, especially this framework that you said in the recent paper where you have extra charge transport. Like that
Yeah.
sounds literally just like what happens in quantum Hall. And I think, there's also something weird about locality for quantum Hall, because if you're on the torus and you cut the torus up and then you look at the boundary of that torus, you get something that has a central charge. So you're not supposed to get the Drinfeld center.
I
But then
see.
on the boundary, there are non-local kind of stuff that kind of does things to the spin chain on the boundary, which is it's a flux basically, and that should kind of violate these additional constraints that you're talking about. Yeah. I think it would be nice to work it out explicitly.
Interesting. Okay, very interesting. Yeah, that sounds very interesting.
I have a few questions. So, in this framework, can you have something similar to Jones-Wasserman subfactor? Can you expect to create new subfactor or to discover some new model of subfactor like Jones-Wasserman for conformal nets?
Yeah, so I think probably not, because it's kind of like in the CFT setting where you have this nice abstract framework, but the only examples that we have, we have to kind of build by hand. And but the good news is we have a lot of examples, but all the examples are constructed from subfactors, like hyperfinite subfactors that we know. So like somehow like it's a nice general theory that actually has more examples. Like in the Wasserman case, it's so hard, even though we can build these examples with loop groups to prove they actually work. In this case, we have lots of examples that we can prove work, namely all the stuff from subfactors. But all those examples we can analyze, the input is hyperfinite subfactor. So I don't suspect you'll actually get new subfactors this way. If anything, yeah, no, I would just say no. It's more like we're using old subfactor theory to do some kind of new physics stuff. That's the way I'm thinking about it. I'm like applying subfactor theory from the like the 90s and 80s to try to apply it to do new things in physics directions. But yeah, I don't see the direction going the other way. I don't see us finding new subfactors. But maybe.
Can you the other question? Can you explain your what permit to reach you to this framework? What was your mind path from your
How did I get here? Oh yeah. So I was at a conference at American Institute of Mathematics. This was in 2023, so it was almost 2 years ago. And I was talking with some QCA people. So in particular, Zhongwan Ha was there, and it was explaining QCA. And somebody asked this question about QCA on symmetric subalgebras. And I immediately was like, oh, that sounds like a subfactor question, because those symmetric subalgebras, they're just these things we do in subfactors. And so I just started thinking about it from that. And then I was like, okay, well, like if you have this automorphisms, what can I make them act on? Well, there should be something like a DHR category. Does that exist? Oh, yeah, like it just works. So you write down the DHR category. It's like the same thing. Oh, is it the Drinfeld center? Yes, it is. And that was a little harder to prove. But that's how it went. Is like basically people at this QCA or people at this event at AIM, there were physicists talking about QCA and this kind of question about dualities, and that's how I started thinking about this. Yeah. So
my last question is: do you have some horizon or some expected application for that? Do you expect something very? What do you have in mind when you think about that? Do you have a direction in mind or a horizon of something?
Yeah, this is a fantastic question. I think that I always come up with new ideas for directions. Right now, I just got back from a big program in Santa Barbara about generalized symmetries, and so it was run by these. Mostly, when I was there, it was mostly string theorists, actually, or I guess I don't know if they still count as string theorists, but I think I saw Liang Kong is here. You were there as well. Actually, a lot of the stuff I learned about SymTFT and things I learned um, from Liang Kong there. Thanks for that. But yeah, basically one thing I've realized to do is using this framework, you can take all the SymTFT stuff people are doing and kind of do it precisely in abstract spin chains, and so you can use this to do a bunch of classification results for stuff that people talk about in SymTFT. Now you have a rigorous mathematical framework for doing SymTFT on the lattice, like completely rigorous. Basically, this algebra B is what you would call physical boundary, and then Lagrangian algebras in the DHR category basically correspond to the pieces of the gap boundary that you do in the SymTFT picture. So now you can just pipe in stuff that people say about SymTFT, turn it into a precise math question about automorphisms on operator algebras, and try to prove it. So that's kind of my program. It's my secret way of learning physics is to try to turn something physicists are talking about into a math question I can understand, and even if I can't prove it, at least I can bash my head around it and try to understand the physics there. So that's my plan is to kind of keep pushing on that picture of thinking about this as like a framework for doing SymTFT on the lattice and see what falls out.
So you defined one invariant like the index for the QCA, which, and
Yeah,
my
so
question is, can you define as Elliott type invariant for QCA? Means you have already defined Elliott invariants for I think actions of fusion categories on sister algebras, right?
yeah. So I mean, that would be super interesting. So I would love if there was like a complete, nice Elliott invariant for trying to classify QCA, like that whole idea of trying to run the Elliott program, which
Mhm.
classifies, C-star algebras up to isomorphism. If you could run it up to bounded spread isomorphism or something like that. And I've thought about it a bit. I don't know the answer. So that second thing is a very good question. I don't have an answer. I mean, maybe this is the answer. Maybe this invariant is the thing. Like you take the index and the DHR. It certainly works in some cases, but I suspect it's missing something. But anyways, to answer your first question, how do you define the index? Is that was that your first question, Mainak? Like, how do you define this index?
No. My question was so whether the Elliott yeah, invariant is defined some kind of standard, not standard invariant like things for QCM.
No. So I think,
For
I think this piece. So these are two homomorphisms. Ind is like a homomorphism to the multiplicative reals. DHR is a homomorphism to braided autoequivalences. Take them together. That pair is at least a piece of something like an Elliott invariant because it at least classifies these things in this case of kind of this when you have on-site group symmetry in the regular representation. Now, it's probably missing something, and I don't know exactly what it is. Like the reason that this works is because the regular representation is super nice and has fell absorption. If I put a different representation in here, this is probably wrong, and I don't actually know how to fix it, and so I don't know how to do it in the general case either because I don't even know how to do it in the group case. So there should be something else to answer your question. My guess is that this conjecture is wrong, and there's actually like a mystery component, and so maybe I should conjecture actually this, but it sounds better when I conjecture this, and then say it's true in a case than it does when I say, this is probably not right, but in some case it works. So anyway, but my true conjecture is this is a piece of the invariant, and there's something missing, and maybe there's some kind of K theory stuff some kind of K-theory way to think about it, because if you go back to the GNVW classification and you look at this, this is actually, this group that classifies the QCA in this case is actually the group of Morita autoequivalences on the UHF C-star algebra up to approximate unitary equivalence or something. So I forget the exact equivalence ratio. But this group, this appears in K theory. So it could be that actually the right way to do this classification is some K theory thing, and somehow just we're accidentally catching pieces of it with this index and this DHR stuff. But somehow probably instead of using index, which is just a number, there might be something more behind there, like a whole Morita equivalence that we're only seeing a shadow of when we take the index, and that could be the right thing that classifies. So that my guess is something like that.
Thanks.
So you talk about conformal nets. I'm not familiar with conformal net. It's the same thing as a critical lattice model, which is a conformal field theory.
Yeah. So a conformal net is generically, so there's chiral conformal nets or more just generally conformal nets where you have, so these are, basically it's the algebraic quantum field theory way to talk about, you take a 1 plus 1D conformal field theory, maybe rational if we want to be nice, and then you take a chiral piece of that. Think about it maybe living on a light cone or something like that, and you take the operators, you take diamonds kind of localized along the light cone, and you get a net of von Neumann algebras on the real line. So it would be a net of von Neumann algebras in the real line. So for every interval inside R, I would have some von Neumann algebra, A sub I, and it would satisfy very similar axioms to what I was talking about. If I is inside J, then A of I is sitting inside A sub J. The main difference, besides just being over R instead of Z, is that everything's actually acting on a Hilbert space H, and there's a special vacuum vector in that Hilbert space. So there's a Hilbert space representation of everything. There's a projective unitary representation of the diffeomorphism group of R, or more precisely of the local diffeomorphism groups of R on the Hilbert space, and it kind of is covariant with respect to the algebras, right? So like if I have some diffeomorphism on R, if I apply the unitary representation, apply an operator localized in I, and then apply the conjugate, that give me an operator localized in whatever, and then the key thing that if you do this chiral story where you take it all on a light cone, that's really hard to build examples of, is you want the generator of the translation on R to be positive energy, which is really chunky. So there's a bunch of technical conditions, but basically, yes, it's a way to talk about 1 plus 1D conformal field theories where you do like a time, you can either, so this was doing a slice along the light cone. You can also do a version where you do a space slice. So I cut along here and define my algebra associated to this interval, what the whole conformal field theory would assign to this light cone, say, this double light cone. And that's what you assign to this interval. And then this is also a conformal net, but it's not positive energy conformal net. So anyway. So yeah, the idea of a conformal net is to get at this kind of time slice or space slice or some slice of a 1 plus 1D conformal field theory. And this generically, you're meant to, if you take a chiral piece, it doesn't recover the whole thing, right? You need 2 chiral pieces and then like a Lagrangian algebra in the C tensor D reverse or whatever, with equivalence. But anyway, was that helpful?
Thank you. The question that I'm interested in is to find the critical point. So for example, in the Hamiltonian that you write down, there are two parameters that you can change, the J and H, right? So I know that when J equals to H, the system is in the Ising CFT. That point is the critical point. So you have the Kramers-Wannier duality here. So can you use the self-dual point of this Kramers-Wannier duality to find the critical point?
Great question. So I also was thinking about that like literally today. And my problem is I don't understand. So everyone you read in the literature and all these papers, everyone talks about Kramers-Wannier. And then they say, oh, and because J, like it's a symmetry when J equals H, then that must mean there's a critical point there. And I don't understand that part. So I don't under so maybe you can explain to me like why does Kramers-Wannier duality being an exact symmetry at the point j equals h imply that that's where the critical point is? Like I haven't found that argument actually written down in the literature, except in Kramers and Wannier's original paper where they use some very special things about easing that they already know. So I would love to be able to do that, but I don't know enough about how you use Kramers-Wannier to get that to argue that j equals h is a critical point. But if you could just somehow give me some general abstract argument about why the fact that that's a fixed point under this duality implies that it's a critical point, then yeah, you should be able to generalize that to all these examples because I can write down all kinds of dualities on these fusion spin chains. In fact, I can kind of parameterize all of them, if you will. And so you could write down all kinds of cool things that switch the different parameters and do all kinds of stuff. I just don't actually understand the argument about getting critical points. So maybe, but yeah, I'm not sure. But I think that's a really, really interesting question.
Example, I'm working on this project, but in another physical system, that is called strength coordinator, which creates a two-dimensional lattice model. And the input is also a fusion category. So we are using something similar to Kramers-Wannier duality to find the critical point. Create a 2D CFT.
Great.
Yes, I wonder whether there is something or thing in your system.
Probably this is something closely related. Yeah, probably this is like maybe like you know how you can take the classical 2D icing and when you push it down with the transfer matrix, you end up with transfer field icing. I wonder if you take your classical thing built from a fusion category, if when you do a quantum thing on the boundary with a transfer matrix, if you end up with some kind of duality like this, that would be very interesting to see.
Yes.
Do you have a paper already written?
It's in progress. It's in progress.
Okay. Definitely send that to me when it's done because I would love to look at that. That sounds very, very interesting.
Yes, sure.
Is it related to this stuff by like Dave Asen and Paul Fendley and their sort of?
It's related to their paper. Yes, but it's a different generalization.
Okay. Very cool. Very cool.
Thank you.
Yeah.
Hi, Corey.
Oh,
Can I
hey,
ask a question?
how's it going? Good to see you.
Sorry, I was late, so I wasn't able to catch I missed the main body of your talk.
Oh, that's okay.
I just want to confirm that you can recover the dream field center of the fusion category directly from a 1+1D abstract spin chain model, right?
That's correct.
So a few years ago, we have a formulation of what kind of this type of dream field center should occur. You mentioned that Xiaogang would call it the patch operator or something.
Yeah.
We have no idea what he mean. I actually didn't even know. We wrote paper together, even with Xiaogang. We call it some kind of a topological sector of symmetric operators.
Okay.
I feel when I look at the last few page you wrote in this because I only attended the last few pages. I only see I feel like what you said is exactly this one, the bimodule DHRB. Looks like this make that story completely rigorous. That's my guess because I don't know what the B is because I probably missed. Would that be something generated by a symmetric operator?
Yeah, exactly. Yeah, that's exactly right.
So I see.
Yeah, that's exactly.
Okay. That's perhaps exactly what we had in mind, but we don't know how to make it rigorous, I guess.
Okay, so you should send me this paper because I want to write a paper where it kind of like makes these sort of things that like you are doing and like Xiaogang with pouch operators and also this SymTFT stuff that we were talking about in Santa Barbara. I want to like make a paper that puts it all together. So I would love to see if you could send me your paper that you're talking about.
Okay, sure. I have another questions is that recently I noticed Tianlan
Yeah.
He also wrote a paper present another way to see this dream field center coming out of naturally from an abstract setting of the spin chain model.
Yeah.
I'm still struggling to understand what he wrote in there, but it looks also quite interesting. It's pure categorical in some sense. It's not a very operator algebra, but yeah, I still have trouble to understand it. But maybe if you're interested, you could also take a look.
I think I saw that paper. It was fairly recent, right? The last couple
Yeah, it's
months.
very recent. It's present a dream field center as some kind of a functor category from
Yeah,
tube category.
I remember that. Yeah.
Some kind of a horizontal categorization of tube algebra to category of VAC.
Yes.
Uh,
Yes.
it's yeah, they have the interpretation is that you can see that tube category directly from the spin chain in some sense.
I see. I
I
see.
wasn't able to get what that means, but it's interesting. No, it definitely relate to what you're doing here, I
Yes.
believe, but
Yeah.
it's not the connection is mysterious. Yeah.
Yeah. Yeah. Somehow, like what I'm doing is taking the symmetric operators and pushing it into the thermodynamic limit. But I think if you like do this and take periodic boundary conditions, somehow
Ah,
instead of the thermodynamic limit, there's some duality between those two, and then you kind of end up in a 2B situation when you do periodic boundary conditions. And if you do the thermodynamic, infinite volume limit, you end up in this other situation I'm talking about here, this kind of subfactor.
ah.
But
Can you theory also connect to Franz Verstrick? They have a and his postdoc what is it, Clement Delcamp. They
yeah,
have
yeah,
a
yeah, yeah.
they
Yeah.
have a work to use tensor network to see how this dream field center emerge from in their setting. Do you see a direct link from your work to their work?
I do, but it's only because I've spent a lot of time staring at tensor networks.
Oh,
so,
I see. Oh, I see.
so
Okay.
I see a direct link, but it might just be because I'm just translating everything into fusion category mumbo jumbo, and
Oh,
so
okay.
I do see it, but I don't know if it's just my yeah,
Oh, I see.
for sure.
Okay. Okay.
Okay.
Yeah. Thank you very much.
Oh yeah, yeah, of course.
Okay, so if there is no other question, let's conclude. Ah.